So just to go into slightly more detail on what's happening in each artificial neuron, we have a set of inputs on the left here, and those inputs are all scaled by a corresponding weight that's learned over time. So you can see x1 is then multiplied by w1, etc. And then we take the sum of those inputs. And then we also apply a bias, which is something that can scale up or down the distribution, this distribution, just so we can alter how much we want the neuron to fire as a baseline or not. And then we then apply this nonlinearity sigma, which can be a wide range of functions. And that's important because it allows us to, the nonlinear aspect allows us to model more complex functions. And as part of the, I guess, if each neuron is doing this in the hidden layer, each one could be doing a different thing. So this bottom one, for instance, could be taking inputs from the previous layer, and it could be measuring something like the mean of the inputs, whereas the one above it could maybe be firing if input 1 is very positive and if input 3 is very negative, and it might be ignoring input 2, just to give an example. So each one is extracting a different high-level feature, if you like, from the original features. And when I say feature, I just mean an input parameter, like, for instance, heart rate or blood pressure or anything like that. Okay, so I've just taken the equation that we had on the previous slide. Sigma can be a range of different functions, the most common of which is the ReLU, or rectified linear unit. If we want to increase the modeling capacity of the model, we can simply stack more layers, or we can make each layer wider. And essentially any network with 2 or more layers is considered to be deep. So that's what the deep learning part means.